The topic we're going to discuss is how does a device, in this case a PC or a phone, knows when to send packets to the default gateway. The default gateway is typically your home broadband router, or in the case of an enterprise network or a service provider, it could be your L3 capable switch or a router. Now, the formula for this is quite simple. From the device perspective, which is the PC or the phone, what it's going to do is it's going to just check if the source IP and its net mask, if it's not equal to the destination IP and the net mask that you're trying to reach, then we know that those packets have to go directly to the gateway for it to take it forward. Because the device thinks that when this formula is true, it means that the device does not know how to send that packet, so it has to rely on the gateway, in this case the router or the switch. So that's exactly the formula that is highlighted here, as you could see here. So this is just in simplistic words without any expression. So if the source IP and the net mask is not equal to your destination IP and net mask, the device, in this case the PC or your mobile phone, would typically send those packets to your local Wi-Fi router or a routing device, any routing device. Now, below is an example with a simplistic diagram again to emphasize how this happens. So you could see there is a PC on the left, which has got an IP address of 192.168.126/24. That's typically a class C address in the private range, but this is just for sake of explanation. And we see that the gateway router has got a 192.168.0.1. Again, this is a /24. That's the gateway IP address. And imagine if the PC1 is trying to target a content server that has got an IP address as 3.3.3.1. Now, if you look at the formula above that we discussed here, it's very clear that the target address that I'm trying to reach is not the same as what I have for my source. So that itself is not matching. Obviously, the target mask in this case is available, and the source mask, in our case, the source mask is 24 and the target mask is /30. So the formula clearly says that these two addresses are not equal to each other, which means the PC now understands that packets to that destination has to be sent to the local router. That's exactly what happens on every home computing PC or your mobile device when they're connected to the local Wi-Fi. They just have to do that. Of course, there is an element of DNS, but we will not focus on DNS in this topic. This topic is pretty much to just explain the basics of how a device knows when to send a packet to its gateway router. Now, there are a few examples that are given here as to how this can be explained further. Now here you can imagine if I have a local network as 192.168.0.126, that's my device PC IP address, and I have a local mask as 255.255.255.0, and imagine if I'm trying to reach a target IP 192.168.0.240. Now, just looking at these three parameters, what we can easily find out is this mask is quite easy because it's a /24, as we know. And there is room for 256 addresses within this network, of which 192.168.0.0 is actually the network address, and the last address 192.168.0.255 is the broadcast address. So everything from 192.168.0.1 to 192.168.0.254 are valid host addresses within the subnet mask. So thus as long as the first three octets, 192.168.0, are actually matching, it doesn't matter what the fourth octet is. In this case, it could be from 1 to 254. So it's very easy by looking at the source address and the destination address that this is actually from the same network. So I don't really have to rely on the gateway to send packets between this source address and this destination address. Now, another use case here is again the same local source IP and the local mask, but the target IP here is 3.3.3.2. Now, this is outside the network purely based on the formula, and when we have a quick scan of the details given, it will send packets for this target IP to the gateway router for it to be routed and taken forward. Now, another example, which is quite interesting, is about VLSM, which is the variable length subnet mask. Now, what if you have your local address as 192.168.0.4 and the local mask is not a 24 or not a /24, as you could see, it is a /29, which is going to give you the new subnet mask as 248. Now, if you look at it, the local mask, because it is a /29, there are valid 8 addresses within each network. So of which the first network will be 192.168.0.0, or we can even call it the zero network because it's a VLSM. And within this network, the broadcast address is actually 192.168.0.7 because the next network is going to be 192.168.0.8 starting off from. So for this case, we have a valid address of 192.168.0.1 ending with the last valid address of 6. Now, easily looking at this, we know that the target IP is not falling within this range. So that indicates again that this is outside my network and I have to rely on the gateway devices to take this packet to that destination. So that is the three possible examples that can give you a simplistic idea as to how a device is really knowing when to send packets to its gateway router or when to do its own decision of finding the target. Now, having spoken about all these things here, now what are the commands available on a PC to quickly find out how my routing table looks like? Now for that, I'm just going into the next page here. Here you can see on a Windows machine, especially on a command prompt, you have a valid command called netstat-r. Now what it does is, in this case, the device on which I ran this command is got an IP address of 192.168.0.240. Now you can quite easily see that it's listing the routing table of the PC and it's telling for any unknown network and any unknown mask, I have to go to my gateway router. In this case, my gateway is got an IP address of 192.168.0.250. And the interface through which I can reach the gateway is my local interface, which has got my local address. That's exactly what is being depicted here. Now, some interesting observations here is, if you look at it, like any broadcast within my local network 192.168.0.255, I'm going to send it on the link, which is, I don't really have to depend on sending my broadcast to the routers, because routers will never ever forward broadcast further down the line. So this is just indicating that anything local that I have to send a broadcast, say for an ARP or whatever, you could be relying on your local link as long as the network is of your same subnet mask. That's what is happening here. Another example that we could do is this one here. Just look at this routing table, 192.168.0.0 and then mask is 255.255.255.0. Now what it is telling is the first three octets are being pretty much the same, but the last octet is variable 0 and 0. So what it's telling is any valid addresses from 1 to 254 is reachable via my own local link. I don't have to really send it to the gateway. This is the example that we spoke previously. Now on a Mac machine, similar command, netstat-r. Now the interesting bit here is I've just used a N, which is for no resolution. That is, if you don't have it on certain devices, they can resolve the gateway IP address to a DNS name. So for the ease of understanding, I've used an N to not resolve the gateway IP address and just display the gateway IP address as it is. Now again here, the same logic, there is a default route telling any unknown destinations will be sent to the gateway. Now an interesting display here on the output is an ARP timer. Now Windows machine or Mac machines pretty much have similar concept. So as soon as you identify ARP entry for a particular IP, you have a MAC address. For example, in this case, 192.168.50.1 is my gateway router and I have found the MAC entry for it. Now I try to keep this entry for 1200 seconds. That's the 20-minute mark. Now from there I count down to 0, within which if I get another ARP, I will reset the timers. If I don't, I will have to re-ARP and learn the entry again. Now this timer is just telling me that for the next 20 minutes, I don't really have to send ARPs to find out the MAC address of my gateway. That's what happens even on Windows. Now these timers are a bit high on end computing devices like PCs because you don't want to be constantly sending out ARPs. Now in terms of a switch, you may have a lesser timer. Sometimes some switches, when they also do the same functionality as ARP, they may just have a time of 300 seconds. It is purely dependent on how the device is deployed and what role the device is performing. Usually on PCs, it is a 1200 second timer. So hope this was useful, just to give you a small heads up as to what is really happening from a device point of view and how it's able to send packets to the gateway router. Thank you. Bye for now.